Okay, before we get back into saponification, just maybe as a way of review, or where did we leave off? Did we look at, we looked at hydrolysis, reaction of an ester with water. Did we look at this ester? We did. I don't see it here in my notes, so just wondering if we did. Here's an ester. Did we look at the hydrolysis of that ester? No? That look, we did?
We named it, but I'm not sure we went through the reaction.
Okay, well we named it. So so the name of this is isopropyl benzoate. So there is your general reaction. An ester plus water forms a carboxylic acid and an alcohol. So, with that general idea, what acid would we get, what alcohol would we get if we reacted that ester with water? Now we talk about it as acid hydrolysis, and that's just what we're indicating right here. So in the presence of some acid, sulfuric acid, hydrochloric acid, just making that solution acidic, it'll hydrolyze. And
Benzoic acid?
all right, so benzoic acid. Now what you need to do, remember what we got here. Water is this, HOH. So an H is going to go on this. Here is your carboxyl group. You get part of the water right there, and the other part of the water right there. Okay? So you get benzoic acid and isopropyl alcohol. We got a general reaction, and I'm just saying any particular ester, you just need to follow it through. It's going to break right here. This is going to break right here into a carboxylic acid and an alcohol. Yeah, and then be able to name these products. So we got benzoic acid, and you got isopropyl alcohol. The next slide has a pretty simple one here. Why is this simple? Well, both the carboxylic part of this ester and the alcohol part of this ester are 3-carbon compounds. So propanoate becomes propanoic acid and 1-propanol. All right, this can't become isopropyl alcohol. You've got it attached here. So right where it is attached is where the OH is going to come in. You've already got hydrogens here. So you're not going to get an OH here to make an isopropyl alcohol. Yeah, so get it into the alcohol form with the right configuration. Here it's bound onto an N carbon. That's where the OH is going to add to it, on the N carbon. And you'll get 1-propanol and propanoic acid. All right, so that's acid hydrolysis. I think it'll be less confusing if we just refer to this as saponification. Base hydrolysis is kind of, and I don't know, this is a picture, from the publisher. This is a picture, so I have a hard time modifying this, but I don't like that picture. I would prefer to see the sodium hydroxide here as a reactant. That's what it is. It reacts. If you look at the difference between this and hydrolysis, so here's your saponification, here is your hydrolysis. And they are actually pretty similar. Not a whole lot of difference. You get a salt over here and an alcohol. You get an acid over here and an alcohol. All right, you got NaOH, so you get an Na. You got HOH, or water, so you get an H. All right, so it's real similar. Both of them are producing an alcohol, but they're producing, in one case, the carboxylic acid, and in another case, the salt of that carboxylic acid. This is saponification. This is hydrolysis. I'm just showing them this way just to show there isn't a huge difference. We have some different names for them. There are some different behaviors of this versus this. This is more soluble in water. It is actually an ionic salt. It doesn't mean it's any of them are soluble in water, but it would be more soluble in water than the carboxylic acid version of that molecule. This is pretty polar, but this is actually ionic, which is another degree of polar. All right, so there's saponification. This is the soap making reaction. This is a reaction to make soap. Some of you may have heard me talking about being in South Africa for a number of years. One of the things I was doing there was teaching at a Job and Life Skills Training Center, teaching people how to make soap. And a little bit of personal history there. I learned that here, because I lived here for three and a half months before I went to South Africa. Lived here in San Antonio. And so I knew I was going to go there and teach how to make soap, but I'd never made soap before. So went over to HEB, talked to the butcher in the back, and I said, you got about 5 pounds of fat? Can I have about 5 pounds of fat? And so they gave me a big bag of fat, took it home, put it in a pot, and boiled it, and mashed it with a potato masher to get all the oils out of the fat. Now what I was doing is basically what the pioneers did when they had to make their own soap. I was saying, well, okay, let's see, how did they make soap? So mashed that down, poured it through a cloth, the water and the oils drained through the cloth, threw away all the gristle and all the leftovers, put it in the refrigerator, and the next morning it was in a big pot, so I had this big round slab of lard, nice white hard lard, and under the bottom of it was water. So whatever water was left over settled to the bottom and was there, but the lard solidified, and that's what I started making soap with, that and sodium hydroxide. But the sodium hydroxide is a reactant. When I was younger, you'd go into a store when I was a little boy, Mom would come home with bars of Phelps-Natha soap. I don't know if you can probably go into hardware and buy something like it. It's pretty rough soap. I mean, you wash with that and your hands feel dry and rippled, and you think, oh man, skin itches. They probably have more sodium hydroxide in there than you would normally have in a bar of soap. If you put a soap recipe together improperly, you'll wash your hands with it and then you kind of itch a little bit, because actually there's some lye left on your skin, and it's very high pH. It eats away at the skin, so it doesn't feel good. If you used laundry detergent was like that, you put a shirt on, and even if it was maybe rinsed, and you'd say, this shirt kind of itches. It actually, the soap is too harsh. So you really gotta get soap down to. Well, we'll look at how you make soap here in a second. Here's the start of it. So how do you make soap? Well, that lard that I would have had in that pan was triglycerides. It would have been triglycerides from beef fat, which has a large component here of stearic acid. This is a triglyceride. We'll do a deep dive on this in chapter 17. But just as we're introducing saponification reaction, it's worth doing it here. So if you started out with lard and sodium hydroxide, you can see the triglyceride is an ester. It has 3 fatty acids attached to the backbone by an ester linkage. You got your carbon-oxygen double bond. Okay, so we've got an ester linkage here. Another one right here. And another one here. So this isn't the fatty acid portion of it, but this is coming from a fatty acid. If you were to hydrolyze this back off of here, you'd get 3 fatty acids and glycerol. And typically in nature, triglycerides here, have 3 different fatty acids attached to them. They don't just have one. They have 3 different ones. So you can see steariol, that would have been from stearic acid. If you clip this off of here, you get stearic acid, linoleic acid, and palmitic acid. 18 carbons. I don't know what this is. It's probably 12 or 14 carbons, and I think this is probably 18 carbons, but it has 2 double bonds in it. So 3 different fatty acids on the glycerol. And there's your glycerol molecule there. It's a triol, alcohol with 3 hydroxyls on it. All right, so when I went to South Africa, we didn't use lard. We used vegetable oils, which that's what they are. They're triglycerides. A bottle of olive oil is a bottle of triglycerides. All right? Like I said, in chapter 17, we'll talk about that a little bit more. But here's the reaction. Think of this as sodium hydroxide. And you're going to need 3 of them, because you're going to get a sodium, and a sodium. It could be potassium hydroxide. The M is there just saying a metal hydroxide of some sort. Sodium, potassium are the 2 most common ones. Yeah, and so 3 hydroxides, you have, or 3 sodium hydroxides, you have 3 hydroxides, and that's what's going in here. A hydroxide, a hydroxide, a hydroxide. You get glycerol, and then a sodium, a sodium, and a sodium. You get these 3. These are your soap molecules. This is soap. We'll look at that in just a second. Triglyceride, it's getting its name off of this. The triglyceride name is coming from the glycerol, which holds the molecule together. If you went in and got a blood sample and they did a cholesterol panel, what they would call a cholesterol panel on your blood, you're probably too early to be worrying about that, but maybe not. No. But if they did that, they would report back to you triglyceride level, LDL level, HDL level, total cholesterol, and probably a few other things. But one of them they would give you is your triglyceride level. This is not necessarily bad. Your body needs these things. Yeah, but there's a level. If it was too high, I'd say, your triglycerides are kind of high. Or they might say your triglycerides are kind of low. Yeah, we'll talk more about that. There's your soap molecules. All right, and what is soap? Soap is a surfactant, surface active agent. It is a molecule now. You've got to remember, we're looking at, if we were looking at stearic acid, we would have, this big long chain. This is what we'd be looking at. You put it in water, the sodium would dissolve off into the water, and you'd have this carboxyl head, which is water soluble, and you'd have this long nonpolar tail, which is not soluble in water. It's hydrophobic. This is hydrophilic. So you've got a molecule now that has a dual nature to it. It can, it's water loving on one end and oil loving on the other end. And so how does it work as a soap? You've got oils on your hands and you wash with soap, and it emulsifies those oils. You make hamburgers, and you've been making hamburgers with your hands, and you got oil all over them. You rinse them under water forever, and they're oily. The oil just doesn't come off in water. But you add a little bit of soap, and you rub that around there, and what's happening, the soap is emulsifying the fat, the oils that are on your hands, into these little micelles carrying the oil away. It doesn't make the oil soluble in water, it emulsifies the oil in the water. We're not saying that oil is dissolving in the water. It's not doing that. It's being emulsified into little micelles, little particle sizes. Milk is, whole milk is what, 4% fat? So you got about 4% oil emulsified in water. And you have whole milk. Looks white. Why? Because these little particles here aren't allowing the aren't allowing the light to transmit through it, and it appears white. Ends up with a white appearance. I remember when I was working at Dow Corning many years ago, they were getting into microemulsions. Microemulsions. What were those? Well, they made these particle sizes so tiny that now you were down at almost the point at which you really weren't blocking the light. And they weren't clear. They were blue. They were kind of blue, but you could see your hand through them. They were microemulsions. The particle size of the emulsion was so fine that you could see through it. And I'm sure many things that are being sold, cosmetics and things like that today, are microemulsions. They have just emulsified it so well that it's almost like the oil is soluble in the water. It just appears like a solution, but there's tiny little oil particles floating around in there with emulsifiers around them. So soap is an emulsifier.
Is that what they do when they smuggle drugs?
I don't know. I'm not sure what they do. Maybe. Yeah, I don't know. I'll check into it. If I Google it too much, I'll probably get arrested. Why are you so interested in this subject? I don't know.
There's a TV show about that.
Okay. They're probably what they may be doing there is microencapsulation. They're encapsulating it in plastic that they then maybe could dissolve it later and get the cocaine back. It's probably not an emulsion, but it might be an encapsulation of it, something like that. I'm not sure. Oh, let's go back one slide here. Just to point out, if you're making soap, and that's why I say this is a reactant, if you put together a soap formula, you really have to look at what is the molecular weight of this thing, or what is the, what do they call that? They call that the, I think they have a saponification value for these triglycerides. What they're basically saying is, because they're going to have different chain lengths on here, they're going to have different molecular weights. Each olive oil, coconut oil, corn oil has a different ratio of the weight of that oil to the amount of sodium hydroxide to completely cleave this. Why is that important? Well, you don't want any of this left over in your soap, just like I was telling you. It's rough, makes you itch, it's bad. And so most soap formulas will err on the side of about 3 to 5% excess oil, so that when you finally do get when it's totally reacted, there's no sodium hydroxide left. There's a little bit of oil, unreacted oil left. And then that makes for a milder soap. So sodium hydroxide is really a reactant. And you have to do the calculations to get the right amount of it. Homemade soaps will have this in it. This is baby oil. Okay, this is good. This is moisturizing. It's there's nothing wrong with it. Sometimes commercially made bars of soap, they make the soap and then they extract the glycerol out of there and use it for something else. And they sell you just the soap molecules. But homemade soaps, you go to a fair and you're buying some soap that someone's making at their home or at their little project, that has this left in it. And that's usually a good ingredient in the soap, glycerol. Okay, before we move on, let's go back to this same little ester we had a minute ago. And just, I'll tell you what, maybe what I should do here. What I should do is go back. Okay, there's the hydrolysis, okay, of this ester, isopropyl benzoate. Let me just write a little bit smaller here. And let's get that ester here again. This time we're going to do the saponification of it. right below the hydrolysis. All right, the same alcohol. Isopropyl alcohol. I'm leaning hard right now on the similarities between these two. Both the hydrolysis, the saponification, produces an alcohol. The saponification produces a molecule that looks a whole lot like the acid. We just have the salt of the acid, the sodium salt of the acid. So instead of benzoic acid, we're getting what? What do we call that? This is isopropyl alcohol over here on the right. Here was the original name of it, benzoate. It's not going to change.
So just sodium benzoate.
Sodium benzoate, yes. Sodium benzoate. All right, see the similarity and the slight difference? Here's saponification, there's hydrolysis. Okay, so yeah, hopefully on these esters you're getting a little familiar now with, okay, this is going to be, is the carboxyl part of the ester. It's going to stay that way, nothing changes here. We're just adding onto that oxygen. This is the alcohol, what will become the alcohol. Nothing changes here, we just add an OH to that carbon. It's this bond right here that's breaking between your ester, your alcohol, and your carboxyl portion of your ester.
How much heat does it take to do that? 'Cause isn't that
Not a lot. No. When you're making soap, we do it at about 40 degrees, 45 degrees centigrade, just warm, not hot. Yeah, if it just a room temperature, it's a little too slow. I don't know what happens if you get it too hot, but if you do it right at room temperature, it'll take quite a while to start for the reaction to get going. But at 40, 45 degrees centigrade, it's perfect. Which is, not even, your coffee is 90 degrees centigrade. It's close to boiling point. So it's not anywhere even near a cup of coffee or a whole hot bowl of soup. It's just a little bit above body temperature. Yeah, the 1107 lab, we have an experiment on soap. And so when we get to that experiment, you make a little bit of soap, just a tiny little bit in a beaker, and check out reactions with it. How can you convert it back into the carboxylic acid, etc. But I also make a batch of soap. We pour it into a mold and cut it up just before the exam. So that at the exam, everybody can get a bar of soap. So we make a bar of soap. It's NVC soap. It says, let's see, what's it say? Just add water. No, I asked it, just add H2O, actually. Doesn't say just add water. Okay. Phosphate esters. I want you to become familiar with what a phosphate ester is. I don't expect you to write a bunch of phosphate ester reactions or anything, but I do want you to appreciate what we mean when we talk about a phosphate ester. Okay, now if I covered that up right there and changed that phosphorus to a carbon, you should start seeing, an ester. Say, well, that would be an ester. And how do you make an ester? You react an alcohol with a carboxylic acid, forms an ester. Well, you take an alcohol and react it with phosphoric acid, and you get this structure right here, which is a phosphate ester. So we're kind of looking at something like this. We got a phosphorus with 4 oxygens around it. And actually, if at physiological pH, these hydrogens will hydrolyze off of there. It is phosphoric acid, and you'll get a negative charge here. So a phosphate ester usually has about a -2 charge on it in the pH of the bloodstream, or the normal pH of the body. That's a phosphate ester. All right, let's take a look at ATP. This is why this is very relevant and very important physiologically. Adenosine triphosphate. We'll see this structure in chapter 20 when we start talking about nucleotides that go into making DNA. This is one, but it would be adenosine monophosphate would be the nucleotide, just with one phosphate group on it. That would be a nucleotide that goes into RNA production or synthesis, adenosine monophosphate. But here's adenosine triphosphate. So you will see these terms: adenosine monophosphate, adenosine diphosphate, and adenosine triphosphate in articles in Anatomy and Physiology or whatever. Probably already have seen them. But here's your adenosine triphosphate, and so here's your phosphate ester right here. But adenosine triphosphate has 2 more phosphate groups attached to that phosphate. These are pretty high energy bonds right here. So this is an energy storage molecule in your body. Stores energy. Here it is again, adenosine triphosphate. There's your 3 phosphates. If you break the bond there and split off one of those phosphate groups, you're down now to ADP, adenosine diphosphate, and it releases a phosphoric acid group and 32 kilocalories of energy per mole. Per mole of ATP that converts to ADP, you would get 32 kilocalories. That's a good chunk of energy. So your body uses that energy for other metabolic reactions. It's a source of energy. This process here of converting that to that, releasing that energy, and then ATP synthase taking that and reconstituting it back to ATP is going on in your body all the time. Has to be, or you're not alive. As long as you're alive, that cycle is going on. How much does it go on? I've just been studying this a little bit lately. During the day, the body will make about 100 pounds of that during a day. So that doesn't mean you are only, don't get confused here. It doesn't mean you are mostly ATP. That doesn't mean that. It means at any point in time there's ATP being made, it's being converted to ADP, it's being converted back to ATP. Any point in time you might have a half a pound of this stuff in your body. But it is doing that so often, so continually, that it produces about 100 pounds of ATP per day. Almost your body weight is being generated into ATP on a daily basis. All right, so that just be able to identify, what do we mean by a phosphate ester? Okay, this gets us to the reaction summary for chapter 14. There's three slides here that are saying basically the same thing in three different formats. How do you make a carboxylic acid? Oxidize an aldehyde, oxidize a primary alcohol. What do carboxylic acids do? Dissociation. You put them in water, they'll dissociate, make the water acidic. Neutralization, react them with a base. Esterification, react them with an alcohol. And then how do they react? Here's a little word summary of some of those reactions. And then here is the end of the chapter summary. This is repeating, but there's some other thing. We'll talk about some of these other. So there's preparation, primary alcohol, aldehyde, carboxylic acid, dissociation, neutralization, form of salt and water. Esterification, this plus an alcohol forms an ester plus water. It's a dehydration. Hydrolysis, ester plus water forms a carboxylic acid. Saponification, the ester plus sodium hydroxide forms the salt plus an alcohol. Formation of a phosphate ester, an alcohol plus phosphoric acid gets you the phosphate ester. These two are legitimate reactions. Those of you in 1107 were exposed to this week, where the Lucas reagent, zinc chloride plus hydrochloric acid, was a reaction that would convert a carboxylic acid into an acid chloride. So you replace your OH with a chloride here. And then here's the acid anhydride. You'll touch on this when we make aspirin in 1107. We'll take salicylic acid and we'll react it with acetic anhydride. So acetic anhydride, but I won't give you reactions for those two.